In the previous video, we showed how to do a hypothesis test when you're comparing two different population means, specifically in the matched pairs data scenario. In this one, instead of talking about matched pairs data, we're going to be having independent samples of data here. So you take one sample independently from the other one, you calculate your statistics for this first sample, statistics for the second sample, and then we're going to use all of this to try to compare the two population means. So one thing we did in the previous one, we had to calculate the extra variable d for the differences between the two things. We're not going to do that again. In fact, it won't even necessarily make sense to do that again because we might even have different numbers of data points. Maybe one sample has 20 people in it, the other one has 25 people in it. In which case, how are you going to subtract them individually? And even if they had the same number in both samples, how do you know which data point corresponds to which data point to subtract? That situation only happened in the matched pairs data. That is not going to be what's happening here. However, we are going to start off the same way when we're going to go ahead and create our hypothesis testing, and we want to go ahead and do the null and alternative hypotheses. Just like before, your null hypothesis is that the means of the two populations are going to be equal. And then your alternative, the three versions of it, is the first mean is smaller than the second mean, that's a left-tailed, or your first mean is greater than the second mean, right-tailed, or all you know, or trying to prove that they're different in some way. That's the two-tailed test. Now, this time, we have our same setup here. What we're going to do is we're going to calculate the p-value in a very different way. So before, we had to calculate the d, the differences between the data points, and then go in and do a t-test for this. This is going to be a t-test, but our t variable before it was much simpler. Now the t variable is this gigantic mess. Again, your calculator is going to do this for you, but you're going to have to do this thing here, s1 squared over n plus s2 squared over n, and 2 and 1. So it gets to be a bit more of a mess here to try to figure out what's going on with the actual t-value, to do a lot more work here. But like I said, we are going to just use our calculator to do all the hard work for us to find this p-value. So let's go ahead and look at this example problem and see how to put in the calculator. It says a company is creating a new weight loss program that they believe is more effective than one particular program currently offered. They get a group of volunteers willing to join a weight loss program and randomly assign each individual to either their new weight loss program or the old one. The weight loss statistics for the 35 individuals in the new program are x1 bar equals 5.97, s1 equals 3.2. So that's how many pounds they've lost in whatever time period. And the statistics for the old program are x bar 2 equals 5.31, and this should say s2 equals 2.8. And there's even one more extra little error here in my video, I apologize. We also need to know the number of people in the second group, and we're going to go ahead and say there are 40 individuals in the second group. So you need to have really 6 numbers here to plug it into our calculator. You need the x bar and the s and the sample size for the first sample, and the x bar s and the sample size for the second sample. So now that we have all this data, let's go ahead and pull up our calculator here. So when we're trying to do a hypothesis test, just like how we do almost all the hypothesis tests, we hit our stat button, we go over to where it says tests. This time, so before we did just the t-test because we only had one variable after we subtracted them and found the d's, the differences. This time though, this is a 2-sample t-test here because we're using 2 independent samples. Go ahead and enter. And you could do the same thing we did before where you have the list, you put in the data. However, we don't need to do that this time because we actually are given the summary, the X bar, and so on. My first X bar was 5.97. My first S was 3.2. My first N, there was 35 people in the new program. My X2 was 5.31. My S2 was 2.8. And my N2 was 40. So we put in all the data points for the two samples. Hit arrow down here. We have to decide which type of test we're doing here. Now, if I were to go back and look at the problem, we are trying to prove that the new program helps people lose more weight. So I wanted to lose more weight here, and the first sample is the new program. So that means I want the case where I'm trying to show that the mu1 is bigger than the mu2. So I'll go ahead and select that there. Now there's this weird thing that says pooled yes or no. So here's the idea. If you were in a situation where you happen to know that the standard deviation for both populations, now again, not the sample standard deviation, but if you happen to know that the population standard deviation for both populations you're talking about, if those are the same number, then you can go ahead and pick pooled and it will work out fine. It does make the calculation a little bit more straightforward and everything like that, but the thing is, it's pretty rare, if not like ever, that you happen to know that the two populations have the same standard deviation. So it's really just a better idea to go ahead and hit no there and just leave it as no. Don't even worry about changing the pool unless they specifically tell you in the problem to use the pooled statistic. I wouldn't do that. And then we go ahead and hit calculate. And we get this here and we see right away the t value, which we don't need. The p value though is 0.174. So my p value is 0.174, or otherwise 17.4% chance. So again, let's interpret what does that mean. That means that if we happen to be in the universe where the two weight loss programs helped equally, so that their average weight loss is the same number, then there would be a 17.4% chance that we'd happen to get samples like this, where the first one was 5.97, the second was 5.31. So the first sample is higher than the second one, but something like this, or even more extreme than this, happens 17.4% of the time. So that is definitely a situation where the p-value is bigger than the alpha, right? 17.4% is bigger than 5%. So that means that our sample is not very unusual, and that means there really isn't any evidence to try to support the alternative hypothesis. So we say there is not sufficient evidence to show that the new weight loss program is better. Now, of course, at this point in time, let's say you're the one in charge of this center, you could then decide, okay, well, if it's not seeming to be really helping, then maybe we'll stop working on that. Let's go back to the old program and make that better. Go back to the drawing board for another new program. Or maybe you'll decide, hey, sure, this one wasn't enough evidence, but the sample was larger, 5.97 versus 5.31. So maybe let's go ahead and just keep it going a little bit longer, try to do another sample later on and see how that goes. So again, I want to just point out that in this class, there isn't necessarily one right answer and then you're done. Now, there is a right answer that says there's not enough evidence here, but then your overall conclusion at the end could go either way. You could decide then to cancel this new weight loss program and go back to a previous one, or you could choose to continue on because, again, the sample was higher, so maybe if we get more data, we'll be able to have a better idea of the picture. So, again, even with the same data, people can make two different conclusions, and it's important for you to understand the process and how you might go about justifying those conclusions.